So here we're going to look at some filters. Look, the troubleshooting of filters is not difficult, but it is necessary. If you're going to look at the air conditioning side of things and take into consideration all aspects of air conditioning, including the troubleshooting side, there are a certain few steps that you can't skip. One of those, you have to always make sure that you check the filters. If you don't got good airflow, nothing else can be right. So there's no sense in checking the temperature drop prior to checking the filters, because if the temperature drop is off one way or the other, you're still going to have to check the filter. So it always works in your favor to start with the filter first. So you pull the filter out, you look at it. What type of filter is it? Is it a fiberglass filter? Like the manufacturers recommend, like they use to get the actual efficiency of these units, like they set up to use with these units? Is it a poly filter? Okay, much more restrictive. Is it a pleated filter? What's the MERV rating if it's a pleated filter? The higher the MERV rating, the better the filter. As we discussed several other times in previous courses, if you've got a higher MERV rating, which makes it a better filter, then you also have a more restrictive filter. The more restrictive, the less the airflow. So filters are always going to cut into airflow. Any kind of restriction will cut into the airflow. Is it a 1-inch filter, or is it a 4-inch or 5-inch filter? A 1-inch filter will traditionally be more restrictive than a 4 or 5-inch filter, because you've got more surface area on the 4 or 5-inch filter. So there's more area for the air to pass through, and that creates less of a pressure drop across that filter. So let's look at a couple of these. Okay, here we've got a 4-inch filter, but it's placed right next to the furnace. See, now the placement of the filter is just as critical as the type of filter. Now think about that. You've got an opening in the side of the furnace. Okay, roughly 15 3/8 inch opening is fairly close to an industry average for the size of opening in a furnace. So if you've got a furnace that's less than 70,000 BTUs and you're using a 16 by 25 filter, 15 3/8 is very, very close to that. So if your filter was installed right next to the furnace like this, you would probably not be restricting the airflow at all, hooking the filter up right there, because it's the same size as the opening in the side of the furnace. However, if you had a larger furnace, 70,000 and on up to 90,000, well, then you're moving up to a 20 by 25 filter, and the opening hasn't changed much. You're still around a 16 by 25 opening. So in that instance, if you butted the furnace right, or the filter right up next to the furnace, like these two examples, then there's about 4 inches of filter that's going to be straight up next to the edge of the furnace with no opening there. Now, the goofy thing is that will increase the resistance of that filter immensely in the ductwork. But if you were just to take and move that filter away 3 to 4 inches, such as some of the drops do, or just build something that gapped it out 3 to 4 inches away from the furnace, now the air is allowed to move across that entire space of the filter. Even though you haven't changed the opening size in the side of the furnace, you have allowed all the air to move across that filter, so it's getting its proper design pressure drop across that filter. So that's one of the most important things, is not only just the type of filter, but where is it placed in the system. Okay, we've got the old style filters that we see with the cage. Some of them are the old hog hair, some of them are fiberglass. I would say at this point, if you run into them, they're probably going to be the fiberglass ones. And some of them leave a lot to be desired. Very difficult to look at a filter installation like this, where clearly it says that it's made for the filter. You can see the little letters up there at the top of that filter compartment that looks like it spells out the word filter and been cut out bigger, but I don't know. I don't have any good explanation as to why somebody would install a filter like this. Okay, but clearly this is not the way to go. There are some people that I've seen install filter compartments similar to this and then use one of those larger magnetic strips like you would get at one of the home stores to cover up the opening. Still not a great example of how you would install that filter. Now let's look at a few examples of what a good filter installation could look like, or some fittings that would be great to use to install those filters. First one's always going to be the boot, the base. Using a return air base, hands down, nearly all applications is going to be the best approach. You have the best, least amount of resistance in your return air. And in addition to that, it makes it very simple to change your filter. You got a pull-out drawer. They're customizable. So as you can see in this base, there's no cutout for that return air. You've got the drop that comes down into it, but then you make that cut for the bottom of the furnace. So you can size them to all different types of furnace. It's not particular other than for the size of the furnace. Clearly, you're going to probably have a bigger furnace if it's a 125,000 BTU furnace than you would if it was a 70,000 BTU furnace. So physical size, you're able to accommodate that by making your own cutout in the base. And here's a few more examples of what I was just talking about. When you're installing those filters, rather than putting them in a slide-in compartment butted up right next to the furnace to where some of that filter area could be restricted, if you were just to take and move that filter media away just a few inches, so that way air can pass over the entire area of the filter, you'll get the desired pressure drop from that filter that it was designed to get. And don't get caught up that you're not changing the opening in the side of the furnace, right? The science behind it is a little bit deeper than that. So you don't have to have the filter be the same size as the opening in the side of the furnace. I mean, think about it. If that were the case, the amount of air that blows through that's sucked into the blower housing would be a big determining factor as well. And most of those are all about the same size, regardless of whether you got a 45,000 BTU furnace or a 70 or a 90,000 BTU furnace. So the opening inside of the blower housing still hasn't changed a whole lot through the years. Now here is the dreaded dual side return. Once you get up into the 90,000 BTU range, you're required by most manufacturers to have either a base or a dual side return or some combination of the two. Now the dual side return, it is very difficult to find any application in which that's going to look well, like it's done well. This particular application here, it's done splendid. It looks like the duct runs go to different portions of the home and they're sized properly, it looks like, and they're all sealed up. And you've got a wide open basement here, so it's almost cheating a little bit, but it is difficult to make the dual side return look really, really good, and this is a great example of how you would do that. Now, in moving into the temperature drop, which very easily is going to be the second thing that you should check when you're out at the home. The temperature drop, if it's not correct, well, something's wrong. Your airflow is off, your charge is off, something is wrong. So there's a step-by-step procedure here that I'm trying to get at. First, you check the filter. Once the filter is good and in check, then you go to the temperature drop. Now you look at the temperature drop. If the temperature drop is good, you can move on, right? And in some instances nowadays, you've got critical charge units and you have got formalized training that are training you a completely different process of what happens after this temp drop. Okay, so in checking the temp drop, it used to be 17 to 21 was a great temp drop. It no longer is. That's no longer the case. Now the desired temp drop is going to be closer to 18 to 26. So look at it this way. If you go and check the filter and the filter is good, and then you check the temp drop and the temp drop is between those magic numbers, 18 and 26, how much better could you possibly make that unit run? Is there a need to hook your gauges up at all? In some areas of the country, the answer is no. In some of these communal forums that you go into, no. There's nothing you can do to help it. So hooking up your gauges could only hurt it because as you hook up your gauges, there's a small transfer of refrigerant. I'm not telling you not to hook your gauges up, but I am telling you that the thought process has been there for a while as to whether or not that's a necessity out on the job site. Especially now that we're moving into having more and more critical charge units because of modulating compressors and things of that nature. But as far as temp drop goes, it's very, very simple. You're taking your temperature reading on the plenum after the coil. Traditionally, you want to be at least 6 inches down that run, so you're out of the radiant impact of that coil. And then you're also wanting to take a temperature reading down towards the filter in the return air area. So the idea is the return air is going to bring air from the house at one temperature, and then it's going to go through the system and cool it down and dehumidify it and blow it out the other side through the registers. So how much cooling is actually happening there? What's the temperature going into the furnace? What's the temperature coming out of the furnace? That's essentially your temperature drop. Is it 18 to 26 degrees? If it is, then you may just be right along the lines of being good. Looking at your gauges. When it comes to gauges, not a lot of rocket science here. And these are primitive gauges, but I do want to explain the primitive gauges because you need to know what goes into the operation of the digital gauges in order to kind of understand the impact of adding and removing refrigerant and how that actually works, right? So as we go through, we'll see a couple of these gauges, and then we'll also look at a couple of the more modern gauges. But really, in looking at these, you've got two sides of the system. You got your suction side, and you got your liquid side, right? Low side, high side, however you want to look at it. On the left, with these gauges, you have your low side, okay, or your vapor side of the system. And on the right, you've got your high side or your liquid side of the system. Now, these aren't red and blue like some of the traditional gauges are, but that's the nature of what these gauges are. You can tell that one's high and one's low because of the pressure readout along the edge. Right, the pressures read along the edge of all of these style gauges, and that's very important, especially for retrofitting. If you're going to use these gauges, as we have talked about in previous lessons, if you're going to use these gauges for a refrigerant that's not on the center section here where your temperatures are, well, then you'd have to get your pressure readings on the edge of the gauges, take them over to a pressure temperature chart, and then make that correspond to a temperature on that pressure temperature chart to replace what's on the inside. These particular gauges are designed for R22, and because they're designed for R22, I could use them on R22, and this temperature in the middle of the set of gauges is what I'm going to use during my superheat or subcooling. Now, the temperatures have got to correspond to that refrigerant that's in the center of the gauges. If they don't, like I said, you're going to have to use the pressures along the outside, go to a PT chart, a pressure temperature chart, whether it's on an app or an actual physical piece of paper, and make that correspond to a temperature that would replace the temperature for the refrigerants that are inside that center section of the gauges. Now, these particular style gauges have 4 ports. And those four ports open and close independent of each other. The 2 outside ports, of course, are going to allow refrigerant into the gauge section. So you're opening up the hose to communicate with that gauge. Now, the other ports, the refrigerant and the vacuum ports, the vacuum port, of course, is self-explanatory. That's where your vacuum pump is going to hook up. That's valuable because that allows you to pull your vacuum and then shut that off, and without unhooking your gauges and breaking your vacuum, you can then open up the system and begin your charging procedures right then and there. Now, the refrigerant one, the REF port, that's right in the front on the right. Now that's the one you're going to do your recovery through, and then also do your charging procedures through as well. So if you're going to hook up a refrigerant cylinder so that you can properly charge, for instance, you're going to use your REF port, and then as you're charging, you're going to open up your low side port on the far left there, and that's going to make those two communicate so that you can add refrigerant into the system. Okay, so we've cleared all that out, and now we're looking at these gauges for the purpose of superheat or subcooling. Superheat is always going to be done on the suction side of the system, and it's always done with a fixed metering device. Now, if you're using a blended refrigerant like 407C, 427, 422B, MO99, Nu 22, any of those refrigerants that are blended, now the PT chart may look a little bit different. Instead of saying liquid or vapor, it's going to say dew point or bubble point. Okay, the dew point's always on the suction side, and the bubble point is always on the liquid side. Okay, so how do you remember that? I mean, you're looking at these this pressure and temperature chart, and you're trying to correlate Nu 22B to a temperature in the center so you can do your superheat while you're doing a retrofit on a set of gauges that are made for R22 and not Nu 22. How do you do it? Well, you've got to know that dew point is actually your suction valve or your suction side of the system's value. You remember that? I remember dew points on the suction side by duperheat. Superheat is always done on the suction side, so the value of dew point, I can remember that as duperheat. And then on the high side, or the liquid side of the system, that's where your bubble point is going to be done. That's where subcooling and bubble point both are found. So I remember bub cooling. Then I can remember both sides of those charts. Now, as you're doing your superheat, back to the task at hand here. As you're doing your superheat, you're going to have obviously a fixed metering device of some sort, and your superheat is just a factor of the temperature in the center of that gauge, right, where your needle crosses over the temperature in the middle part of that gauge. You also will have a thermometer on the suction line side of the system. So you look at your thermometer on the suction line side of the system, you look at your temperature on the gauge over here, and the temperature on the gauge and the temperature on the line set, subtract the small number from the big number. Don't worry about which one's supposed to be hotter, which one's supposed to be colder. It can't be reversed. It doesn't matter. Okay, it could equal 0, right? So if the coil was completely flooded, either because of the load, temperature application, or because you've overcharged the system, it could be 0, but it can't be reversed. So don't worry about which one's supposed to be hotter or colder. We're not creating a refrigeration system here. We're working on one or setting one up. So take the little number, subtract it from the big number. That's your active superheat. I don't need a chart to tell me that. I can do the math. The math is going to probably be some value less than 20 degrees. Now, on the other side of the system, if you have an expansion valve and an expansion valve only, you're going to check the charge using subcooling. Now, there are reasons that you would also check superheat on an expansion valve system, but not for the purpose of checking charge. That's more for the purpose of making sure that the expansion valve is set up properly, okay, or functioning properly. So the subcooling side of things is all done, or the liquid side of things is all where you're going to do your subcooling. So if you've got an expansion valve, remember the idea behind an expansion valve is to get the same amount of superheat all the time. So checking the charge according to superheat on an expansion valve, not a valid method. However, the other side of the system where you're adding refrigerant prior to that expansion valve, the liquid side of the system, that may vary a little bit. See, if you overcharge or undercharge the system, it's going to show up on that side because it hasn't been metered yet. So with an expansion valve, you will always check the charge with subcooling, and it's always going to be done off the liquid side of the system. So you go to the liquid gauge, there's a temperature in the middle. The subcooling is done just exactly like superheat was on the suction side of the system. Okay, so you take your temperature on the gauge, on the liquid gauge, you take your temperature on the line set on the liquid line side, subtract the little number from the big number, that's your active subcooling. It doesn't get any harder than that, right? The only hard part is now I got to decide, is it good enough or not? And we used to have all kinds of rules of thumb. Okay? Rules of thumb are out the window. They've never really been okay, so we've had to throw them out the window. It used to be a rule of thumb on subcooling was always 12 degrees. Now that's far from the truth. And now you're finding a lot of the manufacturers are somewhere between 7 and 9 degrees on their subcooling. And it really depends manufacturer to manufacturer. See, the difference between subcooling and superheat. With superheat, you're using a slide chart to plug in values to tell you what the superheat should be based on the given values that you've plugged into the slide chart. On the subcooling side of things, you can't do that because it doesn't matter what anything is doing around that thing. It could be 100 degrees outside, it could be 30 degrees outside. The job of the expansion valve is to open and close to allow more or less of that refrigerant into the coil. So you're not plugging values in there because that doesn't change anything. You have to have the manufacturer's set point for that thermostat, and you can look it up on your cell phone or your pad or your computer. Sometimes you can get it from the manufacturer's installation instructions if it's there on the job site, and sometimes you can get it off of the manufacturer's nameplate for the appliance that you're working on. But you have to have the manufacturer's subcooling value that they're looking for that particular unit. There's no way around it. Guessing and rules of thumb, they're just not going to get you there. If you're going to guess on something this critical, then what's the use of doing anything according to best practices, because this is a big one. Here's a look at some modern gauges, right? We've got the field piece S-mans over here to the left, and we've got the testo modules over here to the right. Now over to the left, the S-mans, very, very useful. The one thing that I definitely like about these are the ones that I've used for quite a while. I like that they're still 3-port, like some of the old dial style gauges, and I like that it automatically goes into a vacuum. So if I'm pulling a vacuum and I'm hooked up to the system and I hook up my vacuum pump to that center hose there, then it automatically goes into microns once it gets down below a certain value. And you can set alarms on it so it'll let you know when it gets there. It does all your superheat and your subcooling. It's got several different refrigerants programmed into it. It's very, very handy. Some people, these style of digital gauges are rather large, and some folks don't like that. And it doesn't matter if it's the field piece ones or the testo or the Ritchie ones, Yellow Jacket. It doesn't make any difference. You know, they're all a little bit bulky. But you get into the ones here on the right, the testo ones, that's an animal of a different color. The ones here on the right are 100% Bluetooth. And your manifold is no longer a big old set of gauges, it's on your cell phone. So those communicate high side and low side, and as you'll see next to those, there's 2 clamps. That all communicates to an app on your phone through Testo, and it's got several different refrigerants that you can go through, and this does all your superheat and subcooling. You can record it, you can put it on a graph. These things are sensitive enough that you know, when the wind blows, it'll show up on your little graph. It's really, really some next level stuff. There is one downside on those testo models, and that is there's no way to put refrigerant into the system or pull a vacuum or recovery or anything like that with those attached without buying like a T. Okay, the T's aren't expensive, that's not a problem, but the second problem is they're a little bit bulky for the very small area that your service ports are in. Okay, so you have to get them away from that area. Many of the manufacturers don't have enough room for these things to fit down in there. So what I've done is I've gone and got one of them 6-inch rubber hose, like the Yellow Jacket hoses that have a ball valve shut off on there. And you can use those to take it away and make it a little bit more flexible as well. So it's not rigid, which could over time, if you've got vibration, could damage those Bluetooth devices. So I like both of those. They both have their good points and they both have their down points, but they're super useful. And as far as critical charge goes, you can't get much better than what we've got right here with the Testo ones. If the idea is not to be able to take out any refrigerant from the system, right, because a critical charge is down to the ounce, then you have to use something that doesn't remove charge. Something that just has a built-in thermistor or something like that that can communicate with either an external module or your cell phone or something like that. So these are perfect for that application, and I'm a huge fan. Okay, so let's go through the proper steps for superheat. I think we've talked about it enough, so we're gonna go through it rather quickly. Remember, superheat is always done on the suction side of the system, and the value that you're looking for is the value that's the difference between the temperature on the low side gauge and the temperature on the low side thermometer on the line set. Okay, you subtract those two, big number and small number, the value you get is going to be your active superheat. Okay, in order to make your adjustments, this is a slide rule chart that I've used for years. And this slide rule chart is fairly similar to, I'm sure the manufacturer of this slide rule makes them for countless other manufacturers. So they're very, very similar. And the irony is, for those of you that still work on R22 and 410A, these first two steps, which are all that's needed to actually get your superheat value, those first two steps are identical on the green slide chart or the pink slide chart. Makes no difference. Okay, so as we go through this, I'm going to voice a few opinions here, but it's pretty simple. Really, steps 1 and 2 is all that I will ever use, but I will do you the solid of telling you what steps 3 through 6 actually are all about. Okay, so step 1, we got to have a psychrometer of some sort or some sort of a wet bulb thermometer. Now, you don't have to go out and spend a ton of money. You can have a pocket thermometer, and with a pocket thermometer, you can put a piece of wet tissue around it. You could put a piece of wet paper towel. You could cut a shoestring and then cut off the little plastic end and use it for a wick and slide your pocket thermometer through it and get that wet. Okay, so there's all kinds of ways you can make a wet bulb thermometer. You don't have to go out and spend a bunch of money to do that, but you have to have one for step 1. And step 1, it's telling you the indoor entering air wet bulb temperature. That's a confusing way to ask you, what's the wet bulb temperature in a well-circulated area in the home that the customer spends time in? Right? Because that's really what we want to make them feel good in. If they feel good there, they're going to run the system right. So here, I've actually slid it over to 68 degrees. And 68 degrees, remember this isn't dry bulb, so it's not what you're actually setting your thermostat at. It's what is the actual temperature, the feels like temperature. After you've got the air temperature and humidity factor taken into consideration. So here we've got 68. On a normal 70-degree day, you may have that down into the low 60s or 50s even for your wet bulb temperature. So we've slid that over, and as you slid step 1 to meet your wet bulb temperature, step 2 also slid values over to accommodate. Okay, so step 2 is asking you, what's the temperature going through the condenser coils outside? Well, that's pretty simple. Just take your measurement outside, make sure it's not in the direct sunlight so you're getting an accurate reading. Go down the fixed numbers on the left, right? They start at 55 degrees, they go up to 115 degrees. On our day, it was 85. Well, if I'd have had the forethought and actually went through here and put the value in each of those boxes, like on my photocopy, I should have, you would know that at 68 degrees wet bulb, our step number 1 setting, and at 85 degrees outside, our step number 2 value, it's going to give you 19 degrees of superheat that you should have. That's all I need to know. I don't need a chart to tell me what I actually have because I can do the math. I can subtract the temperature on the gauge and the temperature on the line set. I can subtract those and get the value that I actually have running on the system. I need step 1 and 2 off of this chart to tell me what I should have on there. And then at that point, I got to decide, okay, I'm supposed to have 19. Do I have close enough to 19 to leave it alone? All right, plus or minus 5 degrees used to be the staple. Now I think it's probably a little closer to plus or minus 3 degrees to be more accurate. So what are the rest of these steps, right? After step 2. Now, I'm a big fan of using step 1 and step 2 only. You could take step 3 through 6 and throw it away. I'm not a fan of any of that. Step 3, if you would notice in one of these slide charts, step 3 doesn't match what you just found in step 2. Yet it's labeled required superheat. So it leads you to believe that whatever you did in step 2, that's what's in step 3. Not true. You have to reset your chart at that point. Okay, so whatever value you found in step 2, you have to slide your chart again to adjust it to where it meets that in that step 3 box. Problem with that? There's a problem, big problem. Okay, we just found out it was 19 degrees in step 2. That's the superheat we're supposed to have. Well, in step 3, they only go in even numbers. So you have to pick 18 or 20. Okay, so already it's kind of aggravating. So you pick 18 or 20 in that box and set that. And as you set that step, it automatically changes the values for step 5. Right? Step 4 is telling you, look at your vapor pressure, and step 5 is telling you that's the value that you should be reading on your actual thermometer. See, that's step 3 through 6 is a very, very complicated way to take the value on your gauge, the temperature on your gauge, and subtract that from the temperature that's on your line set. Right? That's a really complicated way to go through all that. That's why I'm not a fan of steps 3 through 6. And in my opinion, you should take a Sharpie on steps 3 through 6 and scribble it all out. Okay, this is what it looks like. Here we're hooking up to a system to actually check the superheat. Okay, and yes, this is primitive. It's a little bit dated looking, but all the values are here, right? We've got our refrigerant. Our refrigerant's hooked up to our middle hose on our gauges. The high side's hooked up to the high side service port, low side to the low side service port. Since we're checking superheat, our temperature measurement is going to come off of the suction line by the service port, which you can see is clearly hooked up there. And we've got a piston in the system, and that's why we're checking our superheat. So here's our superheat values. Okay, we are all hooked up. We're checking our measurements. And as you can see on the thermometer over to the left-hand side, it's about 60 degrees on the line set. And the gauge reading chart that you see in the upper right-hand side is just simply a breakaway from what you would see on the gauges, right? The gauges have the pressures on the outside, temperatures that correspond to the pressures on the inside. That's what you're actually seeing here. You've got your pressures on this chart, and you've got your temperatures that correspond with those pressures. So we got a 60-degree suction line temperature. And on our gauges, we got 130 psi, which if you followed the needle down to the center section, it would be 45 degrees. So 130 psi followed down would be 45 degrees, which leaves us with 15 degrees of superheat. Okay, so our actual measured superheat, which was the difference between the gauge temperature and the thermometer temperature on the suction line, both of those on the same side of the system. All your measurements will be off the same side of the system. You just figured out what superheat you should have. Right now, all you got to do is use the slide chart, go through that step 1 and 2 to figure out the superheat you should have. So you know what you do have, the 15 degrees, and you figure out what you should have, whatever it is. And when you add or remove refrigerant, it's important to remember what happens to that superheat. Okay, so if I add refrigerant to a system that has an expansion valve, it lowers the superheat. So if I'm at 15 and I add superheat, or I'm sorry, I add refrigerant, the superheat will fall. So if I continued to add and add and add and add, it would completely flood that evaporator coil and I would get to zero eventually. So if you're at 15 and you need to be at 11 and you want to be as precise as possible, you would add a little bit of refrigerant and then give it 7 to 10 minutes of circulating time and all the while checking it to make sure that you got a little bit closer to that 11. Looking at subcooling, now we know on the subcooling side, we're only checking subcooling with an expansion valve system. Okay, and when you have an expansion valve system, you're checking subcooling, it's all done off the liquid side of the system, all your measurements. Okay, so you're looking at the liquid line gauge and the temperature in the center of the gauge. You're looking at the liquid line thermometer temperature, and you're subtracting the little number from the big number. It's a very, very simple process. On the subcooling calculator, though, very, very aggravating. I am not a fan of the subcooling calculator at all. Okay, if you look at this thing, the first thing it asks you in step number 1 on the subcooling section, it asks you what your required subcooling is. If I knew that, I wouldn't be trying to use a chart. Right, so that's the first aggravating thing. And then the second aggravating thing is right below that in smaller letters. It tells you your required subcooling is 9 degrees plus or minus 3 if you don't know what it is. Okay, so why would they give you a value like 9 degrees on a chart that moves, as you see here, in 5-degree increments? So plus or minus 3, what they're really telling me, I can't use 6 because I go in increments of 5. So if my value is 9 plus or minus 3, the only thing I can use is 10. And some of the older slide rules actually had something in that big open space as well, and told you to use 10 degrees for everything 10 to 14 SEER and 15 degrees for everything 15 plus. That's obviously no longer the case. We don't have rules of thumb like that anymore. In fact, most of the stuff is going to be below 10 degrees of subcooling. If there's anything you learn from looking at this chart, okay, this side of the chart, other than the airflow section, a little bit more valuable, but on the subcooling part up above, it's not valuable at all. It's things that you could figure out. Right? I know how to figure out my subcooling, gauge temperature, liquid line thermometer temperature, subtract the two. This is what I have. Now the only thing I can use to tell me what I should have is the manufacturer's installation guidelines. I'm going to have to look that up. It's just as simple as that. All of this other stuff here complicates everything we just talked about. So I don't spend any time on talking about this side of the chart really, other than to tell you some of the inefficiencies of it, so that you don't make some of the same mistakes that other people make in trying to follow this. Hooking up to a system for subcooling, as you can see, it's a very similar setup to what we've got before with the superheat values, but this time our thermometer is on the liquid line side, so we're going to be taking our liquid line values. And not a whole lot of rocket science here, right? We've got our thermometer again. Our thermometer is reading 120 degrees, or excuse me, our thermometer is reading 100 degrees, while our gauges are at 418 psi. You can see with the red arrow over here, which corresponds to 120 degrees. So we got 120 degrees off of the gauge. We got 100 degrees off of the line set. You subtract those, and you're going to get 20 degrees total of your subcooling. So do you need to adjust your subcooling or not? Now, that's the next question, really. Now, we talked about with superheat, if you add refrigerant, it lowers the superheat. You can get all the way down to 0. It's the opposite with subcooling. If you add refrigerant, it increases the subcooling, spreads it out farther. So if your subcooling is way too high, then there's a good chance that you're already overcharged in the system. And even though you may have a decent temperature drop, being overcharged means that you've altered the capacity and efficiency of the system. Even if it's a slight bit over time, that can make a huge difference to the customer's pocketbook and the longevity of the piece of equipment.